Feeling okay? Cool. So let's give it another 1 minute. So the reading assignment 4, I've uploaded the 3 papers to the assignment module already, and so the open review entry will be created by end of tomorrow. So if you don't receive invitation by end of tomorrow, feel free to email the TA and me. So this reading assignment is mostly about different types of structure prediction models. So we'll be reading about 3 very popular version of structure prediction, from AlphaFold 3 to Omega Fold, which is a single sequence-based prediction model, and Rosetta Fold all atom, which is kind of a precedent of AlphaFold 3 that fall under the previous generation, but extended to a broader range of molecules other than just amino acid. So yeah, I hope everyone can take a deep read of all of the 3 works and try to think about their differences and like whether they make certain design choices and what's the pros and cons of those. All right, so let's continue talk about protein folding, especially the AlphaFold series. So last time we defined this protein folding problem as inferring the 3D space structures. In terms 3D by structures, we particularly means the position of each single amino acid in the 3D space, and given just the single sequence information as the input, and the protein folding algorithms or AlphaFold type of algorithms are one way of doing protein folding, which is through machine learning, where you give it a lot of input and output pairs with carefully designed deep neural networks and machine learning training algorithms. We're using a black box neural network model that directly map from this input sequence to the output structure through these deep learning procedures. Of course, there are other types of folding methodologies, some of them based on, for example, ab initio simulation, where we try to simulate precisely what the forces are applied to the molecules and how they move in small time scale. And we'll see that such kind of model is still useful in the setting where it can be used to augment the predictions that made by these machine learning models, because there will be like tiny or small errors anyway in the end, right? So don't think of AlphaFold as like the only thing that's needed for this problem. There are a lot of the existing classic methodologies that has their own strengths, and therefore we should like use them in combination, or sometimes choose to like maybe distill information from each other. Just to recap, like protein has this unique definition of backbone chains, where a certain set of carbon NC alpha C atoms will form these unique backbone strings, which we use to model the backbone structures. And there are side chains in each of the amino acid, and they also have different sidechain groups, where each sidechain group is a set of atoms with different kind of torsion angle with respect to the backbone. So the protein folding problem can be thought of as the procedure of first predicting like the kind of coarse grain or where the backbones are, and then like zoom into the sidechain and and finally we'll be able to predict the coordinate of each of the atom across the entire protein. And we define kind of the geometry of protein with these bound angles and torsion angles, and which is kind of the which gives us a unique and very kind of concise representation of the protein. So by modeling just the coordinate of C alpha and these torsion angles, we'll be able to almost know the needed degree of freedom to infer the position of the major atoms in the proteins, right? So last time we kind of have an overview of the AlphaFold architecture, where the input we talked about many times, that comprised of these multiple sequence alignment, which are the homologous sequences we search against the databases. And at the same time, we also have the structure templates, which can be used as additional conditions. But the key takeaway here is we want to model the covariance information between pairs of residues, and therefore the notion of pair representations is very important. It is mostly like the contact map. It is invariant to translation rotations, and this is the representation that has been the core representation that this whole deep learning model is learning. So the deep learning the model has two parts. The first part try to only work on these latent representations, including the single representation and pair representation. We call it evoformer blocks, and there are 48 of them. You can consider basically recycling 48 times as well. And there's a structure module called, at the core of that is the IPA, invariant point attention. So a little bit more detail about these evoformer, which we might went a little bit too fast previously. That there's the axial tension that aggregate information for column and row from the MSA, and there's the triangular update block that try to update the pair track in a way that approximately preserve the triangular equality. So this axial tension, we talked about it many times previously, that basically it's a way of doing kind of chain attention across just the rows and across the columns. And particularly for the row attention, we also add the pair representation bias back to the MSA representation. So the row attention here is slightly different than just a normal row attention, where we do want to use some already known pairwise interaction data as the bias. After pre-processing these sequence level information, we then rederive this pair representation through this outer product mean, where for each pair of representation, we take the outer product, and then we will get this R by R matrix. Basically, for each pair of the residues, we have these latent representation that roughly you can think of that as kind of some information about the distances, but also it try to propagate information among the neighborhoods, such that it has some information about the neighborhood geometry as well. And the triangular update is basically doing the triangular update and attention is basically doing additional, message passing and attention on this pair representation that we try to approximate the, try to enforce these trigonometry inequalities. Particularly the update part is basically for every triplet of the edges, we try to, for each of the item in this pair representation, we try to update each of the item by doing this gating function with respect to the outer product of the two edges that are coming out or inside into that node. And all of these are multiplications, so you can basically consider for every triplet, you multiply them all together. And we do this update for every triplet and for every item in the pair matrix. So we're kind of propagating information from all the edges that can be connected as a triangle. And secondly, we apply attention to further aggregate information, and this trigonometry aware attention basically applies here, where instead of normal attention between ij and jk, we have this additional bias term coming from the third edges in the triangle. So why this preserves the trigonometry is if you consider the first term as the cosine times the basically the kind of some approximation of the length of the two edges multiplied by the cosine of that angle, and you could approximate it by basically rewrite this term into the distance, the square of distance of the three edges. So this term is approximately equal to this term. So therefore, if you have something that breaks the inequality, you will have lower attention weight, and since that preserve the inequality, will have higher attention weight. And again, this step is very similar to the update here. We still do the outer product and try to do this multiplicative update. The only difference is now you have the additional weight that is considering kind of these attention information. So I think there are some studies that try to analyze what this step is doing. Is kind of try to fill in the distance matrix by only knowing the pairwise contact map. So if you only, for example, if you only know things that are within distance of 1, smallest distance possible, and that's the initial contact map that you're getting, right? And these triangle updates are basically try to propagate that information to the neighborhood such that at the end you recover the full distance map between like all pairs. That's kind of approximately what this step is trying to mimic, but not in the exact fashion. And therefore that's why we kind of need this additional, the structured module at the end that explicitly extract the 3D information from this pairwise information. But the high-level takeaway here is everything is computed in the relative fashion, right? It's a pairwise information. It doesn't matter how you transform the whole system or how you translate the whole system. Right? The pair representation is invariant to the SC3 transformations. And we'll try to extract information that also inform us how to make local modifications to a structure, which is also SC3 invariant. And when we add it back to transform the kind of global system, that will become equivariant. Cool. So like this is a kind of high-level summary of the evoformer, right? So that there are particular blocks that just used to grab information from the MSA, and there are communication module that put the pair basically communicate between pair representation and the MSA representation. And finally, we have these triangle update that kind of propagate the distance information to like the global distance. And then these pair representations and the single representation that is learned directly from the sequence are fed into these IPA blocks, which is the sequence, which is the structure prediction module. So there are 3 inputs to the structure prediction module, as we talked about last time, right? The pair track, the single track, and the frames, the rigid body frames that we basically use to mimic where the points are in the 3D space. So before we kind of go back to that IPA module, again, like we want to represent a 3D structure, but if we consider it as point cloud, like and use the equivariant GNN that we talked about in a few lecture back, it's kind of too much overkill, and basically we need to track too many atoms at the same time, and we're not making use of these kind of known structures of these small these units of protein, where we can basically assume that some of it, like the bound lengths and some of the bound angles, can be assumed like known because they're pretty rigid in real life. They won't change too much. So we don't need to keep track of every single point, and so there is kind of the notion of rigid body frames. So instead of tracking each of the points as just a point in the 3D space as a point cloud, we kind of define these small frames. We break the protein down into small fragments, and what we care is how these fragments moves relatively into the final structure. And we only care for each of this frame. We only need to model its translation and rotation with respect to some origin in the space. So kind of the idea of the rigid body not only defines, basically, not only reduce the kind of the degree of freedom we need to model for the amino acid, but it also defines kind of a local coordinate system, which for each pair of the frame, right, each pair of amino acid, each of them has its own local system, which can be uniquely defined. Basically, the origin is always in the C alpha, and you could define the IJK, like basically the 3 also normal axis from the C alpha carbon and the 2 bonds pointing out of the C alpha carbon. And by having these kind of triangles, we consider this. We now break all these bounds here, and then we can consider the protein as a gas of rigid bodies, and the network just want to know where we move these rigid bodies, assuming that we start from just putting everything in the origin, and how we kind of gradually move this rigid body such that at the end it move them into the position that mimics the real protein. And this initial guess, where you put everything into the origin, is not needed to preserve the equivariance. So the equivariance does not come from this black hole initialization, but is what they found to be working pretty well in the IPA. But basically, you can start from any initial guess and just learn how to move them by looking at relatively where the frames are right now, and relatively gathering that relative information to inform each of them locally, like where I want to move. right? This does not rely on the global, like where you put them, this pointer and the global coordinate space. However, this black hole initialization is the only thing that worked well, I guess based on their experience. So this is practically what's used in the second generation of AlphaFold. So they call it black hole initialization because it's kind of absorbing everything into the origin, some given origin. All right, so as I mentioned, like we basically, after defining these frames, we'll be able to derive a local coordinate system where the local coordinate system can be computed using the Gram-Schmidt process, which is kind of a linear algebra process that you could use to define a orthogonal basis. And we know exactly where the origins are and where these ijk axes are pointing at. So therefore, we can contrast this local system to another local system, right? For example, this can be the global origin, some global like origin where you can have like a global translation rotation. But at the same time, if you have two different frames, you can also compute the relative orientation and displacement given the two local system, or like local frames. So I hope that this is kind of the important part that keeps the equivariance. All right, so this is an overview of the structural module. As I mentioned, like we have 3 inputs to the IPA module: the pair representation, single representation. Both of them are IC3 invariant features, latent features that kind of preserve some like invariant quantities about geometry, but it's not geometric features. They're not like vectors. They're not coordinates or angles. Particularly, there are additional inputs which are geometric features, which are the translation and rotation matrix of the frames. And here, actually, you can define any. So basically, they initialize everything in the origin, and then compute that everything later in this cycles. The translation rotation in the later stage will be kind of how you transform it with respect to this origin in the beginning. But as I said again, like you can initialize them in any places you want, and there's kind of the global translation rotation, which is defined with respect to this origin here. So these 3 information is fed into the IPA module. It's called IPA, means that it's an invariance module, and it updates the single representation. So it has single output from the IPA module, which is again a latent feature. So it's not the geometric feature. You kind of lose the geometric feature at this stage, but then you kind of use another network to extract the geometric information back from that latent features, which what you predict is the relative movement of the frame given your current geometry, given your current neighborhood information. So by adding this relative change movement to the frames, you kind of you kind of push the frames to forward a little bit towards a different structure, and by doing this multiple times, you're kind of gradually heading towards the final structure that you want to train. You want to predict, and you can get a loss by contrasting that with the ground truth structure. So I'll go into the detail in a second. But in addition, the single representation here is also fed into another network that is used to predict the sidechain angles. And then after we get all of this information, we'll be able to exactly convert things back into the 3D coordinate space to get their coordinates. So the high level is this IPA module is a invariant SE3 invariant attention mechanism that takes the input of a tuples of rotation and translation, and it outputs a kind of updated single latent representation that we can extract the information back from. So how we keep these things invariant, right? So so the key point is the use of these IPA attention here. But you can see that in this attention module, we try to attend for every pairs of attention is always defined like pairwise, right? So we still care about like for every pair of frames, we have their latent representations from the pair. We have their single representations, right? So these part we don't need to worry about their invariance because they're invariant by nature. And so the only part that we actually need a special design is the part that kind of commingle these geometric informations with these features, with the neural network internal features and the weights, and the final update part, right? So attention usually have two steps. The first step is you compute the attention with key and queries. So we define a version for handling these key and queries within these frames with geometric information. So that's this part. And after the attention, you have to multiply that attention weights with some values. So that part is what this 3 branch is doing. So again, here we need to handle it again like uniquely, because we now need to be careful about this geometric features. So all of these entire IP module is about how we make it invariant in these 2 parts. So again, like the normal like attention between pair and single representation, they're invariant by nature. And the key takeaway here is by doing this update for 2 frames. So this is the global translation rotation of I's frame, and this is the J's frame. By setting up the attention like this, which is the L2 norm of the query and key, these 2 are learned by the neural networks, and they're kind of, you can assume that it takes some input initial guess and apply some like multilayer perceptron to get a vector. And then you can do this kind of product and do this L2 norm. This is you can basically consider this as computing kind of relative distances between 2 frames. So between 2 frames, but it's more than distances. But because of this L2 norm between these 2 matrices is invariant to the global translation rotation applied to the Ti and Tj, so this part itself becomes a SE3 invariant calculation. So this is kind of the derivation of the invariance. Basically, if you apply some additional translation in front of Ti and Tj, and you can rewrite it in this way, and such that this part in the L2 will disappear, and at the end you will have something that's not changing at all, even if you multiply something in the front. So after we get these attention weights, right now we can see that there's Aij, which is a weight. You will now multiply with the values to update the values, right? So for the pair, for pair values and single values, just directly multiply, use it as a weight, and multiply it with the value. So that's kind of normal attention, right? But for the again the geometric attention, so instead of just directly multiplying it with the Vj, it kind of convert things into a local relative system by doing this inverse translation of J and Tj. So basically, you can consider like if you have 2 frames, right? These are the local coordinates. So if you move something from here, so if you have something from here, you unmove it, and then move it from here, you get kind of the relative distance, right? The relative orientation of this frame pointing at the other frame. So this is what these inverse and multiplication of Tj here. So this is kind of the great thing about IPA is if you define this translation rotation, even if you have this local kind of translation rotation of the 2 frames, you can do this inverse multiplication such you can convert the global translation rotation into kind of a local relative translation rotation between these 2 frames. So that makes this part only consider the relative relationship between the current I and the J that it's comparing with respect to, right? And then so the update here will be taking the weight and then taking this relative kind of this vector under this relative system, and then do the aggregation. So this is kind of telling you basically if I look at the relative the neighborhood, the different neighborhood in the space, right? Relatively exchange our geometric information, and then weight that information by the attention weights. And the attention weight here, again, it has kind of the inductive bias where the closer you are, the 2 frames, the higher attention weight you have. So it's kind of like looking at the neighbor, emphasizing where the neighbors are, and by looking at the neighbors, I adjust my position a little bit. So because everything is relative, right? So it doesn't matter if all of us are put into another system. So I always know where I should be pointing towards
given my current location. This change basically is local, is with respect to where you are right now for each of the frames. So that's what kind of these IPA module try to gather the information for. And so at the end, because all of these three updated representations are now invariants, you can just do like linear operations and concate them. And that's what we get as the updated single track. Once we have these invariant information that informed us about where I'm heading the next step, I can use now some additional network to extract the geometric information back from these single representations. And that's what this backbone update module is doing. So essentially, it's so going back to like how we represent these translation rotations, right? So if we want to use the kind of Cartesian space rotation matrix, it's going to be like a 3x3 matrix, which is a little bit hard to deal with in the setup. So what we talked about kind of different bases previously, like the spherical harmonics, and there are actually other bases. I think one of the students asked about that question previously. And AlphaFold actually used a different basis called quaternions. It's kind of like also like a 4x4 Rho matrix that can represent rotations. So the key idea is only taking with the one particular positions in the quaternions, which has a size of r/4. You can uniquely kind of define what axis you're applying rotations and how much you want to rotate. And if you know the rotation axis vector already, which is the case of the sidechain angle prediction, then even with 2 dimensions, you'll be able to uniquely kind of define a rotation angle. So by using this, you can reduce the parameter space to only 4. And so that's what kind of, and for in the AlphaFold case, the first component is always 1. So basically, the network just need to predict the 3 component. So we don't need to go detail into how this quaternion conversion works, but essentially, you have these 3 from this linear representation. You first directly predict the translation from that, which is simple, like because we know that SI already preserves some kind of distance information. And the BCDs are the quaternion, the remaining quaternion that we kind of want to predict using certain rules that applies to like how you derive quaternion. So after we get this quaternion, we can map it back to the Cartesian like rotation matrix and return them, so you can apply changes to the frames accordingly. All right, so after we predict the backbones, we move like the backbone frames. Now the remaining task is how we model the sidechain atoms. And because the sidechains are basically the chemical bound for the sidechains are already known for each given amino acid type. So we can kind of assume that if you know the first, basically the rotation axis is known. So if you know the first rotation axis and you apply the first rotation, then you can uniquely also define the second rotation axis. And so the problem will be solving like the second torsion angles. And similarly, if you know the second one, then you can uniquely define the axis for the third one. And now you just need 2 quaternions to decide to model the angle. So basically, it again make use of a very simple network, which is ResNet, that also basically learn from these single representations and make predictions of these 4 chi-angles, which uniquely determines kind of the sidechain orientation. And again, we're assuming kind of bound length is already known, or we don't need to model them at this stage yet because we have a precise model at the end. We can refine everything a little bit. Yeah, this is just some details about like for different types of amino acid, because the sidechain group will be completely different, right? You have different number of atoms and functional groups, so the chi-angle will be defined uniquely for each type of amino acid. And this information is given in the input sequence already, so you have this kind of rule-based mapping way of mapping the chi-angles uniquely to the atoms of each of the amino acid types. So that's why, like, given these backbone positions and their orientations and the sidechain chi-angles, we can uniquely map, we apply some rules, we can uniquely map these frame representation back to the 3D coordinate system to get the coordinate of each single atoms, which is what the normal kind of PDB file gives you. I think that the equivariance is kind of helpful here is that like the PDB file can be recorded with any possible global coordinate system. So being able to compare with any training data from different system will make the training, hopefully makes the training easier by injecting this inductive bias. So it is kind of one of the exact equivariance is contributing to. But again, like there's approximated version which is in alpha 3 we'll talk about later, that do not use IPA at all, but still works. So it's kind of in a interesting like timing to see kind of how different models could work and may not be needed to fulfill some tasks. So additional step that I want to mention here is after we get the coordinate, we actually have this refinement step where we actually run some molecular dynamics models that try to refine the models a little bit, because these molecular dynamics or simulation-based models, even if they're not very they're not very suitable for a fully ab initio simulation sometimes, because it takes too long to get the simulation to actually fold things into the final stage, or there could be so many uncontrollable variables that are not known in the dynamics that may accumulate these errors when you run these long simulations. However, if you're already close to the global optimum, it is still like the molecular dynamics can be used to take a step further towards the true optimum. So therefore, it's actually a very commonly used strategy to apply additional either force field or kind of more like classic molecular dynamics on the final prediction of the machine learning model. And this step is kind of obliviated in a lot of the papers, machine learning papers. You will see like people don't talk about this a lot, but actually a lot of the papers, actually they need this refinement step at the end. But if the goal is just to get the good thing at the end, it doesn't matter like if it's your network that predict everything, or you combine any methodologies together. So like anything that works will be the final like approach that people take. Similar thing applied to kind of small molecules, right? A lot of the small molecule generative models, they don't need to give you the most valid structure at one shot, because you can always like use open Bibles or RDKit to kind of move the things around a little bit to be more valid. So there's a mindset, line of mindset that like maybe we don't need to have that precise modeling, but just kind of give a reasonable prediction is good. All right, so and we talked about last time that the model, although it's okay to train just a supervised learning model, but a lot of time we want a model to be kind of uncertainty aware, which not only helps maybe sometimes the model to generalize better, but also let the users to be. So it would be very good if the users can know how confident the predictions are to inform their decisions. So there are two confidence metrics that AlphaFold 2 is predicting. AlphaFold 3 is actually predicting something more. But for these two confidence metrics, we can consider like the first one called PLDDT. It's called a local distance difference, where you basically it's a score from 0 to 100. The higher, the better, and it tells you like how much well aligned your predicted structure is with respect to the ground truth structures. And sometimes this is computed only between the C alpha carbon. Sometimes it's predicted for every single atom if you really care, like really precise predictions. But I think the AlphaFold default is just computed for C alpha. This is actually a very interesting phenomenon that like AlphaFold is really able to predict its own error pretty well, even though it's not able to predict the real structure. But when it's making a mistake, it's very likely that it knows that it's making a mistake, and therefore, like when we talk about protein design later, we will see people using the PLDDT as almost like an in silico metric to decide whether your design protein is good or not. Basically, like if AlphaFold is confident in predicting such protein, you can consider this kind of fall into the true distribution that is trained. It's used to train AlphaFold, and AlphaFold can generalize well. But if it's not very good in terms of PLDDT, then you just throw them away. You don't do experiment on them. The other thing is the PAE, which is instead of doing a single residue prediction, we kind of do pairwise aligned arrow. Just to mention that every time we compute these arrows, we have to do alignment first, where we have some algorithm that kind of different from the sequence alignment, which you can introduce gaps, but here you kind of just want to apply the translation to your two, because you have two sets of points and you try to find the alignment that gives you the minimum error between the two. And there are like known algorithms that can be used to do this alignment. So when we compute these metrics, we always do alignment first, right? And then when we align, we compute these distances, either pairwise or singlewise. So so that's the PLDDT, and the model actually predicts more than these. They also predict what we call distal map or histomap. So it's kind of like for every pair of atom, we know their ground truth distances, and it might be helpful to like check if the model kind of is able to, at least like learn this information well. So as an additional auxiliary, the model also learned to predict distograms. And distogram, so distance map and distogram only difference by, like if you call it distogram means you discretize the distance maps by like certain bins. So you can bin this continuous distance into like sometimes 24, sometimes 64 bins, and just assign like a one hot value to it. And so you can train it with kind of cross entropy loss instead of doing the regression loss. There might be additionally like some like experiment-related metrics, like when you solve the crystal structures, you could have like additional information about how accurate your structures are, like B factors. Some of these can be also made as a prediction task. So now going back to the structure prediction, right? In able to train a model, we have to define some loss function that compares your predictions with the ground truth structures, right? And this is a very important decision that needs to make. So one naive approach is just compute the distance, right? Either like align before aligning it or without aligning it, just compute the means, the RMSD between every pairs of corresponding atoms. This might work, but computationally, like it's not very robust, and also it does not take into account the chirality. And furthermore, although like kind of our system is kind of invariant, it's still like not ideal if like everything is in absolute space and you have to kind of memorize a lot of different patterns of moving things towards different positioning of the coordinates. So alternative to RMSD, AlphaFold used something called FAPE loss, which is also a very nice, interesting metric, only available because with the definition of these local frame structures. So what it does is for every pair of frames, you could compare basically for every pair of atom or residues in the true structures and the predicted structures. You again can apply this inverse translation to get the relative positioning of the frames with respect to another frame's local coordinate system. So then now the task here is basically for every pair of frames, I compute the relative position of the ground truth and the predicted frames, and compare like how close these two vectors are. So it's kind of like also computing the loss with respect to this relative information, right? Which is what the network is supposed to learn to memorize. And this precisely recovers the full 3D relative structure. If you predict all the pairwise well, you should predict also the structure well. And interestingly, this loss is also able to distinguish different chiralities. So kind of the people find this loss to be much better than RMS, the root mean square loss. And this is what's used not only in AlphaFold, but training a lot of other structural related machine learning models, including the diffusion models that we're going to also study a lot later in this course. Okay, so FAPE loss is of course the most important loss of the structures, but it's not the only loss, right? Basically, the final loss function of AlphaFold have two stages. The training stage where it kind of use just the PDB data, and it's a fine-tuning stage where it trains for fewer epochs, but and maybe with additional data, but has some additional like loss term that try to regularize the space better. So initially, the training loss that are used here is the Phase loss and the average Phase loss and torsion angle losses. So this is the auxiliary loss. And the discogram prediction, which, as I mentioned, you could easily make it a cross-entropy loss because you have one hot. And they also did additionally try to train this MSA module better with this mask MSA loss, kind of like what we used previously talk about MSA transformers and exactly like what MSA transformer is using to train this MSA module. And so yeah, so this is kind of what how AlphaFold 2 is kind of enforcing the contribution from MSA track, because otherwise the model could just directly memorize the distances without even looking at this evolutionary information, which may limit its generalization. For example, if for a new protein, it's totally different sequence space, where you have some evolutionary information, you want to enforce the model to look at this information, right? And additionally, there's this like experiment-related outputs, which is only introduced during the fine-tuning stage, and this violation loss, which is kind of an interesting thing that like it's hard to imagine that only with the frames you can preserve the bond angle, between two amino acids pretty well, and how can you that just making this relative movement and you're not making any clashes because you're not aware of where the atoms are, right? So this is a question that I think when AlphaFold people give talk, people ask a lot, and so the first answer is actually the model is really smart, even if it's not knowing like where precisely the atoms are. It inherently kind of know to avoid clashes. But secondly, they do use this clashes loss as additional loss in the fine-tuning stage to kind of fine-tune, give like the final refinement of the model if it actually making these small errors. I think the violation loss will be more than just clashes, but maybe some other like illegal bound angles or bound distances. But I think this part is not very important according to the AlphaFold team, and I think it's even removed completely from the AlphaFold 3. But as an auxiliary task, we can in real like computation tasks, some people do include some of these constraints, and a lot of time they don't help with training, especially for generative model, and they sometimes can hurt the training, and which is still like I guess a little bit mysterious, like why is such the case. All right, so another important concept that's introduced in AlphaFold. I think it's probably one of the first, but maybe you see such recycling happening maybe in some other like smaller models. So for example, like antibody design, people maybe do also an iterative update as well. But I think the formal definition of recycling comes out at this AlphaFold 2 model, where instead of trying to do everything in one shot, we try to gradually modify our result by taking multiple steps. This is a little bit like the IPA module, where kind of you start from the initial guess and you move it with like 8 times gradually to the last to the end. So what this recycling is doing here is you basically do everything start over from beginning, but the next time you make use of the information that you predict in the first round. And how you do is you add these predicted structure information back to the pair representation and the MSA representation. Because we know the pair representation is basically your initial guess of what the structure could be. And without this prediction, your initial guess only come from the MSA and from this template, if you're able to find a template. But if you already make some predictions, maybe that predictions is better than what you have already. So we want to kind of use this as a guidance of the next round of prediction that maybe I could do a better job in the next round. So this is kind of the original recycling idea, and in AlphaFold 2, it actually applies 3 times of the recycling. And you can basically do this with a special setting of this slope gradient, so you can basically propagate the loss through this recycles of 3 iterations, even though you're going through the network, like the same network 3 times. And you can see that indeed it improves this recycle. The recycle improves the model structure predictions, and it's actually adopted in a lot of these earlier structure prediction models. So for example, Rosetta Fold also use recycle, and multiple tracks and the recycling of multiple tracks as well. Cool. So now we talk about data sets. Of course, there are like some solved crystal structures that are very accurate from the protein database, but that's still not a lot of them. And we know like how much more sequence data is available in real life compared to the solved structure data. So AlphaFold 2 uses this very smart trick of distillation, or kind of it's kind of like the self-distillation in machine learning, where basically what distillation means is you're training the model with your own predictions in some way, such that you try to make use of the noisy information of the landscape that you learn and use that to improve the robustness of the model. So this distillation loss is not exactly the structure prediction loss. I don't include some detail here, but normally when you apply this distilled data, you don't try to let the model predict just their label, but you try to preserve the local robustness of your prediction. So, questions?
How come this sort of augmentation doesn't lead to load collapse?
Yeah, so like I said, like you're not letting it to learn from this data as a prediction task, but you apply a robustness loss, which try to smooth out the prediction landscape. We're basically saying if you make small perturbation to your in-distribution data, then your predicted label should not change. And that's what the kind of the noisy student kind of training is doing in the normal like machine learning distillation. So you're not forcing it to precisely predict what it predict, right? Because that's not giving you anything. It's just like if you know that under certain manipulation of the data space, your prediction should not drastically change. And I think in the AlphaFold case, the manipulation and the robustness is actually coming from the PLDT prediction. So I think what they want to do is like, I think based on the MSA prediction, and so there's one distillation loss is so one augmentation loss is they gradually decrease the MSA information. And they're saying that with you gradually decrease MSA information, your prediction should smoothly becomes like, so your prediction should be smoothly becomes more uncertain. And I think a lot of these prediction loss, they are also like, so first of all, they're not using all the predictions on the sequence data. They have to also threshold their predictions by their PLDT. So only the very confident predictions are used to enhance the data set. And secondly, they applied additional distillation by doing some augmentation to the input data. Particularly, the augmentation is applied to the MSA block, just try to enforce kind of some local robustness to the reduce the information, evolutionary information. And this distillation trick is actually, I think there's a theoretical analysis on how much distillation will help. And I think the conclusion is it will not help, like, it will not monotonically increase your performance. It will only increase your performance up to a certain round of distillation. So there's a paper from Chong Kyung-hyun in NYU. They kind of theoretically analyze the gain the generalization gain from training with distillation set, and explicitly prove that at the beginning you can get some initial boost to the generalization, but after a certain round of self-training, you will actually lose generalization. And if you train for too many times, then you will, like you said, maybe mode collapse and actually go into like overfitting and not generalize pretty well. So there's kind of a sweet spot where the distillation will help. And honestly, this thing actually is very useful. I would see like the Rosetta 4 team training their model as well, and they also found the distillation set to be helping. It's just a matter of how you construct the distillation set to give it really like good examples and not hallucinated examples, and how you set up the loss carefully so we don't kind of catastrophically forget and do like mode collapse, like you mentioned. All right, so just one little blob that they actually, the AlphaFold 2 paper conducted this ablation study where you kind of remove each of the different component from it. And I think, as I mentioned, the thing that is really important here is the triangle updates. And so I think this is where you remove a single part, like basically remove the part on the y-axis. So if you don't have the triangle updates, it kind of drastically worsen the performance. And so that's why kind of these triangle updates are kept for AlphaFold 3. And everything else, actually, they're not that important. And the conclusion from the AlphaFold team is that every component matters, and it's the combinatorial effect of all of these designs in the network that makes it the best performance at the end. But I think that the key part that makes this really works is this triangle update. And here it's showing that if you don't have IPA and recycling, the things doesn't work. But I guess if you only remove IPA, it's kind of still doing okay compared to if you remove the triangle update. So the recycling is actually what matters here a lot. And this recycling idea is important. Basically the idea of gradually decoding and predicting these things instead of doing a one-shot prediction is important. And that kind of motivated the change that are effectively taken in AlphaFold 3, right? So, which is the kind of the diffusion, the diffusion module. So before that, we kind of revisit their very phenomenon prediction accuracy at that time, where you see that this GGT is kind of the basically approximately how much of the data you could predict well. And AlphaFold is kind of 2 is give you a very drastic boost to this metrics at that year, and the kind of the prediction error in terms of Armstrongs, where if you have errors of 1 Armstrong, it's really impressive because you can model these key atoms, C alpha atoms, RMSD, with less than 1 Armstrong error. So it kind of does so much better compared to all the baselines in the previous years. So that becomes really phenomenal and groundbreaking work at the time. But this CASP data set is still going on, and additionally there are additional benchmark, which right now we call it post-busters, which is again another kind of very commonly used benchmarking data set right now. A lot of the recent structure prediction tools benchmarks with post-busters. And they actually expand the amount of structural data by making predictions on the existing natural sequences, and created this database called AFDB, which is used to augment a lot of the structure-based model as well. For example, the recent generative models on structures, they sometimes try to also use AFDB as the additional training set to fit the generative model too. Although this data set could subject to biases, prediction biases, because it's not perfect, but it's already very helpful for a wide range of tasks. I think ESM Fold has similar thing they call ESM Atlas or some meta atlas that also gives you another source of additional data that could be used to if you want to take into consideration the structure information. And there are several later methods, or probably back-to-back work that came out at a similar time, including the Rosetta Fold, which I think one of the reading assignment would be about the Rosetta Fold all-atom version, but the methodology is very, very similar to AlphaFold, except that there's slightly change in the architectures. And ESM Fold and Omega Fold, these are kind of another realm of method, but the main difference is you replace the MSA by just using a language model. And the good thing about that is kind of you don't need to always rely on MSA, and of course a lot of the de novo sequences or some unnatural sequence or orphan proteins does not have MSA. And OpenFold is kind of the open sourced version with some help from I think ML system folks. I think the goal here is to make AlphaFold reproducible, everyone can train it by themselves. At the same time, they re-implement some architecture of AlphaFold such that the training efficiency and inference efficiency is improved by a lot. For example, the deep speed kernel is one of such one of such architecture that is used, which significantly accelerate the triangle attention computation, which is very, very expensive step. And if you're interested in using these methodologies, you can just search online. They have like OpenFold, and CoLabFold is another platform. You can basically fold anything you like within the Colab's Google Colab, and it's free, and you can also try to play with that. So of course, there are also some limitations. For example, like the PDB training data is like still pretty small relatively, and the performance. There are a lot of like later work that's analyzed AlphaFold predictions, and they actually see that AlphaFold does not perform well in bigger proteins, larger complexes, because it does not scale. Also, it is very bad, like not very good at predicting loops and like disordered regions. And if you remove the MSA, and for some like disordered regions or things that are very complex in nature, like enzymes, if you remove the MSA track, they basically cannot fold pretty well. So you need to at least give it some guide of like this part should at least fold or be contacted to each other, and some small like hints of like hotspots to make it really able to fold like nature like complex proteins. But it's working so well on the de novo proteins, which are a lot of like helical bundles, or things that with a lot of alpha helix and beta sheets. So, so still, it's very powerful tool, not just prediction tool, but also like a validation tool to check if your de novo design is worth to try to going to the next stage or not. People still use AlphaFold in the single sequence mode without MSA to test out the de novo designs. For example, the ones designed by David Baker's lab, and they found the AlphaFold 2 metrics like PLDDTs and RMSDs to be very good ground truth. If you want to check how good your designs are. Okay, so now let's talk about AlphaFold 3, right? So earlier this year, AlphaFold gets a great update. Now it's become AlphaFold 3. And there are a couple of basically key modifications, but I think these modifications all have a source that you could trace back to their ablation study. Right, so basically, if we look at these AlphaFold architectures, it has recycles everywhere. Like the evoformer has like 48 recycles. Basically, you do it 48 times, it kind of like 48 recycles. And this entire structure prediction plus MSA module, like evoformer module, is also recycled for like 3 to 5 times. And the limitation here in the previous AlphaFold 2 is that first of these recycles, these evoformer blocks are super computationally heavy, and we'll talk about later like why it's heavy. It's not just because of the triangle update, but also like the MSA module that need to always keep track of the MSA, which is a huge data. So it really cannot scale for large proteins. And what they're training with is this crops of proteins, of like the smaller crops of proteins. If you have a too big of a protein, I think it's about the size of like 300 to 400 amino acid. And the second thing is this prediction is kind of deterministic. Like if you make some arrow early in the stage, you can just like follow that arrow, and you will only have like at the end of a training, you only have one shot to make a prediction here. So this might not be the best, considering kind of the model uncertainty thing we talk about, right? You could, if you have kind of a notion of uncertainty where you're predicting kind of a distribution, that it's likely, the chance is likely that if you hit something unknown, right? If you hit it with multiple shots, you could increase your shot of hitting the right thing. So, so these two intuition gives them the modifications that happens in AlphaFold 3. Which is, first of all, like the recycle is because it's too expensive. It shouldn't be happening across like all the modules. So they move the recycle inside the pair former and only do heavy recycling within the pair former, and keep the structure prediction as just one last time, the final step of the structure prediction. And secondly, instead of doing the kind of the prediction and recycle and IPA module, they replace this with a diffusion model. And so this is kind of the details of the models. So so you can see that the recycling only happens here. And well, yeah, we'll revisit this module later, but and then here what diffusion module does is kind of you still condition on these pair-former informations, but you don't use them through commingle them with the frames with the IPA module. Instead, you have the diffusion module, which is basically a diffusion transformer model. We're going to talk about details in 3 lectures later. But this is a diffusion transformer module that's commonly used a lot in like vision diffusion for computer vision. And you just start from some random guess, like random positioning of the frames, and iteratively through solving a stochastic differential equation, resulting in a distribution of the final distance. The final structures. And they keep the confidence prediction modules. Well, so everything else is kind of not changed by a lot. So like diffusion is kind of, in a high level, we'll revisit it later, but it's kind of the what computer vision, originated from computer vision, where people find that, for example, if you consider like variational autoencoder being or like a GAN type of generative as being kind of sampling from a Gaussian noise and applying a transformation through a network and give with a transformation you get a sample from the image manifold. But doing that in one step is too difficult, like GAN. So why not doing it in multiple steps? And people find that, yeah, if you want, the goal is to transform from a random noise to an image, you could actually do it with multiple steps. And how we're doing it is we're kind of defining a unique path of transformation where you have this forward path where you gradually crop your image with certain kind of noise schedules and noise. And the assumption is with enough number of timestamps, you'll be approaching almost like a real Gaussian noise. And we train a network to invert this process by doing this kind of learning the inversion of this step approximately at each step. And so theoretically, you have some way of how to train this inverse step, even though it's kind of theoretically like intractable if you directly compute the ground truth, but there are a way of using variational inference to approximately compute this ground truth and do a regression, kind of a matching loss on these stepwise inverse transformations. So what happens here is exactly the same. Basically, you kind of define the probability path from a random noise in the 3D space, which is a Euclidean space, and you apply this diffusion module, which at each time step you basically predict where you are heading towards in the next time step, and by repeating it for multiple times, you gradually denoise the structure into the ground truth structure, which is the final prediction. You can see that it's actually kind of similar to what IPA does, except that IPA start everything from the origin, but here we have a starting Gaussian noise, and this noise actually gives us this randomness or stochasticity by making this a generative model, right? So now if we have the condition that you learn from these pair-formers, condition on the same pair-former pair information, you can sample a different noise to draw like different predictions of the structure, which gives you kind of predicted distribution of the structure. And another small detail is they kind of remove the IPA module. Like they're not using the equivariant structure anymore and directly using kind of Euclidean space, non-equivariant architecture like the IT. But by doing some matching at the end, right? So if you make some random guess and you have a ground truth, if you can just align them, you can always compute some like arrow between the two. And that's what kind of a little bit brute force, but that's what's happening here. And then basically you can augment your data by try out different rotations mainly, not translations, because translation is easy to align, but like different rotations. You rotate your ground truths into different angles and try to find the closest one with your prediction, and just kind of approximately enforce the model to kind of be able to predict structures in all different like angles. And it actually magically works well in AlphaFold 3. And a lot of changes made to the pair track, the MSE track as well. So remember that previously the recycle on this evil former includes these like axial tensions on the MSAs and several triangle updates that kind of each time you need to go from pair track to MSA track and go back and then do this triangle update. So everything needs to be start over from the MSA track, and so the MSA track is expensive, both because the MSA representation itself is a large data representation you need to keep in the memory, and that's kind of cumbersome, and doing it for 48 times is also a lot. So one thing they remove is this axial attentions. So they don't find this very useful, and they just directly apply some initial translations. And so instead of carrying over these MSA for every recycle, they only keep like a short MSA aware like update for 4 blocks. So they only have 4 blocks of recycle that really start from MSA and pair track, and do this full outer product mean and triangle updates, which they preserve exactly the same way as they did in AlphaFold 2. And then once we get this final pair track, we just only do recycle. We can throw away the MSA and then only do recycling on this pair track information with additional 48 blocks of pair formers with triangle updates. So basically, pair former is this thing here, or particularly this thing here, which only have the triangle updates, recycling for 48 blocks. And that kind of saved the compute by a lot and drastically kind of disentangle this the MSA module. And at the end, this pair former proved to be the very important, the most important architecture, the triangular update in AlphaFold 3. And they're also like motivated a lot of the later like generative model structures that also, if you have enough compute, you can basically do this expensive update when you train like a diffusion, like generative model as well. Right. So like after making all of these things, they're able to both doing the normal structure prediction task well, which they already pretty well, but also expand their scope to model like multiple protein-protein interactions, and also generalize the type of molecule they can model into basically any type of molecule they claim, like including, for example, DNA molecules and small molecule ligands and metals. So for example, this is the protein-protein interaction prediction, where the like interaction can be a lot of different things, right? For like solid protein-protein interaction, they're like doing okay with this AlphaFold multimer region. But with this AlphaFold 3, they're like kind of much better because you can consider like 2 proteins. When you solve the folding problem, you're also solving their interaction by like moving them with diffusion and kind of dock them together. And they found that kind of this diffusion, the diffusion algorithm is able to kind of solve that docking problem better than the previous version that used the recycling. And one type of problem that's super hard is the protein-antibody interaction or antibody-antigen interaction, which because of the flexibility of the loops and just like the uncertainty and diversity of the loops in antibody, AlphaFold 2 can't really do well on these jobs. And what's significantly changed in AlphaFold 3 is their capability of predicting immunologues like antibodies and TCRs improved by a lot, and nanobodies also improved by a lot. And even for the monomer prediction, which like they're already good previously, have like slight improvement, which is not the key highlight, but most of the interaction part is what's getting improved. And they also generalize their notion of frames and representations to a broader spectrum of atoms. This, of course, takes a long time to understand, like how they do this expedition. A lot of detailed design is put into how they model, like represent these like small molecule ligands, RNA units as opposed to the amino acid. But at a high level, it's like this idea is not new in AlphaFold. Like Rosetta Fold also have the all-atom version that try to kind of expand the scope into other molecules, which is one of the reading assignment. Yeah, as a result, kind of these two methods got compared a lot, but I think the result is like they show that they're actually pretty good at protein ligand prediction right now, where they use these docking methodologies to, for example, like the structure-based drug design. Like one type of important task in structure-based drug design is like for a given pocket or a given target that has a certain pocket that interact with small molecules, right? How we design the small molecule ligand to inhibit this pocket, or the opposite direction. If you have a small molecule ligand, how we design a pocket to like, wrap around the ligand, interact and interact with the ligand. So this task is solved much better with AlphaFold, and even like without any like ground truth structure, like just with sequence and the molecule, like you'll be able to solve it at the same, solving the folding and the docking problem at the same time. This is compared to these set of methodologies where you don't have, we already have the structures and you just solve the docking with like diffusion and flow matching. Of course, these methods do well because they already know the structure. And right now, the AlphaFold is solving an even harder task. Like you don't know the structure and you predict it and solve the docking, and it can be done like even better than some methods that already have the structure. So it's kind of truly impressive. Although this is the internal data, like no one have the model in hand, no one can benchmark it the same way as they report it in the paper. So yeah, I think AlphaFold 3 still have some issues. I think apparently like a lot of people observe that it tend to give you nice prediction for things that are not supposed to be nice. Like there are a lot of like known, abnormal like proteins which are not supposed to be like folding well. Like they should be just like loops, but somehow like the model sometimes tend to like put things into organized like helical bundles, which can be like one type of hallucination. And this I heard people also argue maybe this is because they kind of removed the clash loss. So like in the original AlphaFold, if you don't regularize by clash loss, sometimes the things that try to so it will try to not push things out. But I think here it's not like try to push. It will always try to like pack things together, and also we have like some issue of symmetry breaking. Like if you and I think in nature you have a lot of symmetric oligomers where you have multiple copy of them, but they kind of interact and form like a loop or like a ball, like based on their symmetry. But because the diffusion is not able to kind of tell like this part of the noise should go to this direction and this part should go to this direction because they look the same, they have the symmetry breaking problem where they just put everything overlapping. They just overlay the same copy of a different subunit if they're symmetric. That can be an issue. And so the improvement on the antibody and nanobody is seen only if you apply a lot of random seeds. So if you sample it for more times, the success rate of predicting the right interaction pattern will also increase. And this is something that very obvious, particularly for antibody type of interactions. And this is also something that kind of might be a good thing, that it actually doing some making better predictions, but also could be a bad thing that you spend significantly more compute to get one thing that works. So yeah, I think this is basic thing that it's like not the end of the game yet, and there's like plenty of space that people can still work on implementations and improvements of the model. And I think this realm of method is kind of a very nice. You can see how their thinking evolves from AlphaFold to AlphaFold 2 and AlphaFold 3, and a lot of these designs are actually making sense given the previous observations. Okay, so I think we're about time. The class will end here. Next we will talk about more protein interactions and protein functions.